I'm Chris Ketelsen. I'm at University of Colorado at Boulder, and this is joint work with Rob Scheichel, who's at University of Bath, and Aretha Tekentrup, who is a postdoc with Max Gunsberger at Florida State University, and Paniot, who's at Lawrence Livermore. And I'm going to be talking about extending these multi-level Monte Carlo ideas to Markov chain Monte Carlo, which is a little bit more difficult of a problem. The model problem that we want to look at, or the application, is doing uncertainty quantification in subsurface flow. And so I'm just going to take a really simple model problem, which is steady state single phase flow, and we're going to do it in 2 dimensions. And the model applications are things like CO2 sequestration, contaminant transport in groundwater or reservoir forecasting. And basically the gist is that you've got this subsurface that you would like to model, and of course you don't actually know what the fine scale representation of the subsurface looks like. I mean, you might have a good idea in some areas from core samples, but you definitely don't know, at least not at the pore level, what it looks like everywhere in your domain. Your domain might be, multiple square kilometers. So instead what you do is you talk to a bunch of geologists or geophysicists, and they tell you what the statistical properties of the substructure are, and then you base a model on that. So the uncertainty is in the substructure, which I'm going to represent in the conductivity field K, and the fact that it's stochastic, I'm going to represent its dependence on the stochastic parameter omega. And because the data is stochastic and has uncertainty, that means that the solutions for the pressure and for the flux are also going to have uncertainty in them as well. And any kind of quantity of interest that we might want to compute based on the solution is also going to have some kind of uncertainty. So there are lots of challenges, and there are lots of strategies that people have tried. So one thing that you could do if you have a nice prior model is you could sample from this conductivity field and estimate moments of this quantity of interest. What we would like to do is take this farther, and in the real world setting, you might have some kind of measured data that you want to condition this sampling on, right? So this might be some information about the pressure in the system, or it might be some kind of flux at a well or something like this, something that you've measured, and you want to take this added real life information in and use it to help you get better samples. Okay? So to do this, you have to sample from this conditional probability distribution, and this requires the Markov chain Monte Carlo. All of these simulations, because it's a Monte Carlo method, require getting samples of this quantity of interest, and each one of those samples requires solving the forward problem, which could be some complicated PDE on a very refined mesh, and this is extraordinarily expensive if you're getting things like millions of samples. Okay? So some things that people have tried, one thing that is due to Effendia at Texas A&M is to just accelerate the sampling process by what they call multi-level preconditioned Markov chain Monte Carlo, and this is basically just a pre-screening process where you use coarse grids and coarse grid simulations to weed out really bad samples before you go and solve them on the fine grid. And so this can accelerate the sampling, but what we're really interested in is accelerating the estimation. So traditional Monte Carlo estimation is notoriously slow. We saw in Hillary's talk that the root mean squared error goes like 1 over the square root of the number of samples, and so every time you want to get an extra digit of accuracy in your estimator, that takes a tremendous amount of additional samples and a tremendous amount of additional PDE solves. So if you have simple priors, so you're solving the Monte Carlo problem, not the Markov chain Monte Carlo problem, you can accelerate this with multi-level Monte Carlo, which you're all now experts in. This is due to work by Andrew Cliff and Mike Giles and Rob Scheichel and Heinrich, who all applied this to different applications kind of, since the early 2000s. So what our goal is to extend this to accelerate the estimation of Markov chain Monte Carlo. So I'll go through this kind of fast because Hillary just did this, but we're trying to estimate some kind of quantity of interest, and if I just did this in a regular Monte Carlo setting, I'd take a whole bunch of samples of the conductivity field, and I would solve the forward PDE and compute my quantity of interest, and then I just take the average of them. So the convergence in the mean square error goes like, the variance of the quantity of interest divided by the number of samples. And so like I just said, the standard error goes like 1 over the square root of n, and this is super slow. Okay, so that seems to be out of order. We're going to do a really simplified model problem. We're just going to solve the diffusion equation with this random conductivity field. We're going to use linear finite elements on a uniform triangular mesh, and the grid levels are going to be denoted like I've got some coarsest grid level, which I call m sub 0, and then the finer grid levels are going to go up by a power of 2 in each dimension. The quantity of interest I'm going to look at is the effective conductivity through the east boundary of the domain, which is given by this. And for the prior distribution, we're going to assume that the conductivity field is log normal, and that means that the log of the conductivity field is normal, and it's got some 2-point covariance structure given by this function, and we're going to take a Cartan-Love expansion of the log of the conductivity field, and that gives us a way to rapidly generate these samples. Okay? So these mu j and phi j are eigenvalues and eigenfunctions of integral equation that has this correlation function as its kernel. So sampling a conductivity field then means I have to generate R of these normal random variables, and then I just do this linear combination of the basis functions. So now, because all of these things are going to depend on theta now, I'm going to start showing dependence on theta instead of k, but it means the same thing. Okay, so then the sample of doing a Monte Carlo, or the process of doing a Monte Carlo estimate on the fine grid level, which I've denoted capital L, just means I draw n samples of this vector of R normal variables, compute the conductivity field, solve the forward problem, compute my quantity of interest, and then compute a Monte Carlo estimate of this. So the mean square error of this guy goes like this sampling error, and then this is the discretization error. And what this means is that if I want to put some kind of tolerance on what my standard error is, I want it to be less than epsilon, then I need each one of the terms in the mean square error to be less than epsilon squared over 2. And that means that I have to drive both of these terms down. I need to do many, many samples to drive the sampling error down, and I need to use a very fine mesh in order to drive the discretization error down. Okay, so multi-level Monte Carlo. I'm going to take this expectation of this quantity on the fine grid that I'm trying to find. I'm going to write it as a telescoping sum of this quantity on subsequent consecutive meshes, and just for ease of notation, define y to be these correction terms. And then what I'm going to do is run independent, and it's really important that they're independent Monte Carlo simulations for each one of the level-dependent estimators. And when I get an approximation or an estimate of all of these things, I just sum them up, and that's my estimate for the fine grid. Okay? So the reason that this works so well is that here, this is the sampling error for the multi-level Monte Carlo, and because so these corrections, the variance in these corrections are going to depend on the approximation properties of your mesh, and as you go to finer, finer, and finer mesh, then the variance of the fine level corrections are going to get really small, and that means that I need very, very few samples on the fine mesh in order to drive that sampling error down. Okay, I don't know what that did. Okay, so what do we do for Markov chain Monte Carlo? So now we're going to suppose that we have some kind of real world data F, and now we want to sample from the posterior distribution, which is the prior distribution conditioned on this real data. And we do this in the usual way, using Metropolis-Hastings. So I use Bayes' law. I get a likelihood function which has this form, and this F is the actual data, and this F sub L of theta is what we call the model response. So I plug in a sample of the conductivity field, I run the simulation, and then I extract what the predicted values of this real world data is, and then I compare them. So this sigma squared F is what we call the fidelity term, and this controls like how hard we want to enforce that the model data matches the real world data. So to draw a sample, we are at some state theta n. We propose a new one through some transition probability, and this could be like a random walk. And then it's an accept or reject method. So you either accept the new sample as a good sample and actually throw it into the mix, or you reject it and you don't use it at all. So the probability with which you accept a new sample is given by this expression, where here this is the posterior distribution, and what this just says that, If the probability of your proposal is high, then you're going to accept it. And if the probability is not high, you still might accept it. And this allows you to jump out of all these local minimums that are in the probability space. And you do this, 1,000 times. And after you've done this, then all the samples after that, after this, we call this the burn-in phase. After you've done this, then these theta samples that you're getting are coming from the posterior distribution. Okay, so here are some probable transition probabilities you could use. You could use a random walk, or you could use this preconditioned random walk, which actually gives you a little bit better acceptance rate. And if you use something like a random walk, which is a symmetric transition probability, then calculating this alpha simplifies quite a bit. Okay, so now we want to try to do this in a multi-level way. And so I would naively try to write down the telescoping sum. And here I actually have to indicate with the subscript L or the superscript L where this posterior distribution is coming from. Now, because the posterior distribution involves this accept-reject phase, the accept-reject phase depends on solving the PDE. That means that the actual posterior distribution depends on what level you're doing the simulation on. Okay? Now, if I try to do the telescoping like this, so this would be bad. Because each one of these simulations depends on you doing this on the fine grid. So you don't want to do this. This doesn't save anything. It makes it tremendously more expensive. So instead what you would try to do is you try to do these Markov chain simulations on the coarse levels, but that gives us another problem. And that's that this thing is no longer a telescoping sum. If you look at two adjacent estimators, and you look at, these are the things that are supposed to cancel out, but this thing is sampled from the posterior on L-1, this thing is sampled from the posterior on level L, those things are not going to have the same expectation. Okay? So this is going to create a tremendous amount of bias and basically destroy the method. So what we want to try to do is, if I just look at one of these level-dependent estimators, is I want to sample the theta in this guy from the fine posterior distribution, and I want to sample this guy somehow from the coarse posterior distribution. But at the same time, I need this variance to go down. Otherwise, this is where we get the gains in multi-level Monte Carlo. So I need to somehow do this in a clever way so that this decays with L. Okay? So what we're going to do is, and this is something that's standard in regular multi-level Monte Carlo too, is that I'm going to truncate the KL modes as I go down the levels, because many of these things are high frequency and can't be represented on the coarse levels anyway, and they just kind of cause noise. So we would do this anyway, but it's convenient for the Markov chain stuff. What I'm going to do is I'm going to define this auxiliary chain that I call capital theta that lives on level L-1, and it's got R L-1 modes, which is fewer than RL modes. And then what I'm going to do is try to sample this guy using little theta, sample this guy using big theta, and ensure that the variance of this thing is small. So the way I'm going to do this is a two-stage process. I'm going to sample capital theta L-1 on level L-1 just using standard Metropolis Hastings. And then for the fine grid proposal, I'm going to decompose the fine level stochastic parameters into things that can be represented on the coarse grid and things that can only be represented on the fine grid. Okay? So this theta LC and capital theta L-1 are the same size. They're the same modes. Okay? So to do the sampling of theta little l, I'm going to take as a proposal for the coarse portion of the modes just whatever the current auxiliary sample is on the coarse grid. And then I'm going to sample the fine level modes just in the usual way with a random walk or something like this. So if this proposal on the fine grid is accepted, that means that its coarse modes match exactly the modes in the auxiliary chain on the coarse grid. And because of that, that means that these things should be pretty similar, okay? Because they match at least in the modes that matter on the coarse grid. And that's going to mean that this variance of this level-dependent estimator is small. Okay, so the actual algorithm for the coarse chain step, this is exactly Metropolis Hastings on the coarse grid. Okay, they changed the little thetas to big thetas. Okay? For the fine step, you're going to propose the new sample or the new parameters exactly the way that I just described. and I'm going to compute this accept-reject ratio. It looks like this. And now this transition probability is a little bit funny. It depends on kind of what's happening on the course grid. So this is the probability that those course modes would get proposed on the course grid. This is the probability that they'd get accepted on the course grid. And then this is the usual transition probability for the fine modes. And you plug all this in and you do a tremendous amount of algebra and you get something that looks really nice. Okay? It's just a ratio of the posterior distributions on the fine grid and the one on the coarse grid. Okay, so, and then you plug it into just a normal Metropolis Hastings algorithm with all of those things defined. And then at the end of this, you compute this level-dependent estimator using little theta L and big theta, L minus 1. So this is a non-standard transition probability, but it doesn't really matter. We can still prove that at the end of the day, after sufficient burden, this little theta L's are still coming from the correct posterior distribution. Okay, so some subtleties. Well, this hopefully wasn't that subtle. These things are all coming from the correct stationary distributions, the distributions we want. Something that happens in multi-level Monte Carlo that's really nice, or something that's, sorry, I should say, anytime you run a Markov chain Monte Carlo algorithm where you're doing some kind of intelligent pre-screening of the things that appear on the fine grid, what happens is you get an enhanced acceptance rate. Okay? So usually if you do this for standard Markov chain Monte Carlo, your acceptance rate that you kind of turn the knobs until you get something that's like you accept 25% of them, which is, that's okay, but you're still throwing away 75% of those results you got from solving a PDE, so you're wasting a lot of stuff. What happens when you do this kind of pre-screening is that the acceptance rate goes up. And we like that because that means we're sampling better and we're getting more new information for a cheaper cost. And now this level-dependent estimator samples are small for most realizations. So there's 4 possible things that could happen if you run this 2-stage proposal. Let's assume that we're starting from a position where big theta and little theta, the coarse part of little theta, are in sync, they're the same. So there's 4 things that could happen. You could reject both of the samples, in which case they're both still very close together, because they were before. You could accept both of the samples, in which case they're both close together, because this thing got the proposal from here. If you reject on the coarse grid and accept on the fine grid, then they're still close together. And then the bad part is when you accept on the coarse grid and then reject on the fine grid. And then these things are going to separate a little bit because the coarse modes are no longer going to be in sync. But the nice thing about this is that you carry on, and the second that you accept on both levels, which happens very quickly, especially because we've got this increased acceptance rate on the fine grids, they snap back together. Okay? So what's going to happen is this is going to make the variance of the level-dependent estimator a little bit higher than we would like, but this happens so infrequently that it does not break the method by any means. Okay? And in fact, for the simulations that I've done, it happens on less than 1% of samples. So some future work that we could do, there's this another method called delayed rejection Markov chain Monte Carlo, where if your method does tell you you're supposed to reject a sample, what you can do is propose another one, and propose another one, until you accept something before you go back and actually throw that sample into the mix. Okay, so this would dramatically reduce the amount of these, what we call drift events. And that's something that we're working on. Okay, so let's do some tests. So I've just got the diffusion equation on a square domain. I've got Dirichlet boundary conditions on the left and right, and Neumann boundary conditions on the top and the bottom. I'm using a correlation length of 0.5, so this is on the fine grid, this is pretty rough, it's not super rough. The variance is 1, and I'm using 169 KL modes on the fine grid. My data, my real world data, are pressure values at just 9 points that I picked randomly in the domain. Okay, so I generate a reference solution, pick 9 points, sample the pressure there, and just call that my real world data. So the coarsest grid is 16 by 16, and anytime you're doing Markov chain Monte Carlo, you always run what we call parallel chains because the stochastic space that you're sampling from is very large, and you want to make sure that you're sampling all aspects of it. Okay? And then again, my quantity of interest is this effective conductivity. So this shows the decay of the variance and the mean, or I should say the mean and the variance, of the level-dependent estimators. So the dotted line is just what would happen if I ran a regular Monte Carlo simulation on that grid resolution. So you can see that the mean of this effective conductivity on the individual levels is something like 2. And then the level-dependent estimators decay like the mesh spacing to the 1/2. For the variance is the part that we're actually interested in. You can see that the variance, if I just did vanilla Markov chain Monte Carlo on each of the grid resolutions, the variance is order 1. But if I look at the variance of the level-dependent estimators, they're decaying quite nicely, and they're decaying something like h to the -1. So if I compare sample size, cost, accuracy, all of these things, so this is for a given epsilon, so this is a given fine grid tolerance that I'm trying to drive the root mean square error below. This is the number of samples that it takes on each level, and you'll notice that depending on epsilon, I've got different number of levels. That's because epsilon fixes my discretization error, and I'm trying to make the sampling error about the same as the discretization error, and so if the discretization error is big, I don't need that many levels. Okay? So level 0 is the coarsest level, and I don't know, let's just look at one of the higher accuracy ones that involves 4 levels. You can see that on the coarse grid, I'm doing something like, oh, the dots are over the exponents. This is 10 to the 7, so I'm doing about 10 million samples. That's 10 million, right? Yeah, okay. And then as I go up in the levels, I need fewer and fewer and fewer samples, and to the point where on the fine grid, I'm using something like 2,000 or something like that. Now, I showed you that picture that showed that the variance of the quantity of interest, if I was just doing regular Monte Carlo, tended to be order 1. That means that if I was doing this in a single level setting, I would be doing close to that 10 million samples on the fine grid. It's a little bit less than that, maybe 75% of that, but it's still a lot more than 2,000. Okay? Now, if I look at the cost, I define the epsilon cost to be the sum of, it's just all the work that we do in the entire simulation. It's the cost of doing a forward solve on a particular level times the number of samples that I take. And here I'm comparing multi-level Monte Carlo, or multi-level Markov chain Monte Carlo and standard Markov chain Monte Carlo. And here I've normalized by the cost in the multi-level algorithm just so that the exponents are manageable. And so you can see that as the accuracy that we're requiring decreases or gets more accurate, the multi-level Monte Carlo stays pretty flat and the standard Monte Carlo blows up. And these are blowing up the way they are because on some of these for smaller accuracy I need to go to a finer grid, and on a finer grid these things are much more expensive. So only on 4 levels we get a speed up that's order 100, which is very good. And also these things you can imagine will get better and better as you go to finer resolution and use more grids. Okay? So we're extremely happy with this. We should also check to make sure we're getting the right answer. And so this shows 9 different simulations on different fine grid resolutions where I ran this with standard MCMC and multi-level MCMC, and you can see that the final estimators of the quantity of interest agree extremely well. Okay? So it's working. So in conclusion, we've extended this multi-level Monte Carlo idea to Markov chain Monte Carlo, and we've tested the performance on pretty simple model problem for subsurface flow, and the estimates of the quantities of interest agree really well with traditional Markov chain Monte Carlo, and we got up to 2 orders of magnitude speed up. So some future work is we want to try this on real problems, multi-phase flow, Richard's equation, things like this, and then there are all kinds of things out there that use Markov chain Monte Carlo to do their sampling. One of them is lots of things in quantum field theory use this, and these are extremely expensive because these are 4D problems. And then also to try to improve these drift events using delayed rejection MCMC. Here are some references, and here's where the money came from a couple years ago. Yeah, thanks.